All right. Welcome, everyone. Hi, I'm Sangeeta Bhari, Chief Founder at AIFoundry.ai, where we help organizations adopt AI in practical, business-driven ways. I work with teams to move AI from experiments to real impact, fast execution, measurable outcomes, and systems that actually get used. I'm so excited for you to be here for our two-day practical AI workshops. Thank you for joining us, investing your time in learning and building with us. Over the next 2 days, we will be doing two workshops. Today, we are focusing on RAG, and tomorrow we're going to talking about different tools that you can leverage in the software development life cycle. And these are not just concept, but actually how to actually build systems that work with real data and real use cases. We are here to learn, experiment, ask questions, and have fun doing it. And I'm very grateful to share this experience with such an amazing group of participants. Welcome again, and let's have a great two workshops. But before we get started, I wanted to introduce the speakers today. I'm very excited and proud to have Ashima and Reena. I went to school with them, with both of them, and they are superstars. And they make you think. And honestly, it was just a privilege learning alongside them. Fast forward to today, Ashima is a PhD in comp science. She has done incredible work across Meta, A&T Labs, Cisco. She's built AI-driven systems at massive scales, from optimization to rack applications. And Reena is at Microsoft. She's building, great SharePoint experiencing, working on an AI-powered content understanding and practical rack system for enterprise documents. What this makes it even special is that they've agreed to offer this as a complimentary. So, thank you so much. And we are all spent a lot of time building, experimenting, and building this workshop for you all in a way for us to give back. And I hope you will really enjoy the session. I'm going to hand over to our speakers for today. Thank you. I will actually encourage everyone keeps their camera on, then we know, you are present and you are here. Uh, Thank you. All yours.
Thank you, Sangeeta. Good afternoon, everyone, and thank you for joining us for the RAG workshop. And Ashima and I are going to share how the RAG components work, and again, we are going to build a RAG system from scratch. So let's quickly have a glimpse of what actually we are going to build. I'm going to share my screen. I hope everybody can see the screen now. And I have two documents here, one of which is a technical document and another one is the HR policy document. And on the right side, you will see a chatbot system, which we have in our Colab. And this chatbot system where, now I can ask the questions, maybe, about my HR policies or about the technical document. So this chatbot system, I have grounded on these two documents. So that's the chatbot we are going to build today. So in case, I ask what is my remote work policy, and we can see that, it is going to give the answer. I had asked number of questions, I was just testing, and so it is going to say that, how, and the information now comes not from the generic LLM, but it is from the company documents. So yes, everybody, we are going to build this one, and let's go back to our presentation. So this is our 2 hours of agenda, and we are going to move fast, but do not worry, everything is hands-on, and we'll make sure that everybody is hands-on after the workshop on our RAG system. So next 45 minutes of presentation, we are just setting up why and how, so the hands-on exercises make sense. First 10 minutes, quick intro to LLMs, what they are, how they work. Next, deep dive into RAG, what it is, how the architecture works. And then we'll share the use cases, how you can apply in the real world application, customer support bots, code documentation, research assistants, wherever you want to apply. Q&A will try to keep towards the end, but please post your question in the chat and we should be able to answer. We just want to make sure that whatever we have planned, we can finish that. And I hope everybody has done the prereq work, everybody has the Colab and the Grok key, because that's the one we are going to use. So by the end of the workshop, I hope everybody, understand that how they are going to build the RAG system. So we will be walking away with, one is a RAG system, how the one you actually coded, not just watched us build. Second, you will have mastery of core technical components, chunking strategies, embedding vector database, the building blocks of modern AI applications. Third, ready to deploy code templates. You can take these home, swap in your own documents, and have a production ready system running. And finally, the skill to build the AI application for any domain, whether that is a customer support, internal knowledge bases, legal document search, or anything which your company wants to do or you want to do at your personal business. So let's get started. So let's see what makes LLM so powerful. So what are LLMs? Large language models. LLMs are AI models trained on massive amount of data, billions of words from books, website articles, whatever is available online. Think of it like a really sophisticated autocomplete on your phone. But instead of learning just from the texting history, it has learned from virtually everything ever written online. So that's what gives them the ability to understand and generate human-like text. But it is not just memorizing. These models actually learn deeper patterns in a language. So let's see how they learn. So large language models, let's see how they actually learn the three key concepts. First is pattern, relationship, and then context. So what is pattern? So when we say that the cat sat on dash, the model predicts it has to be an object where something can sit on. So it has to be like a mat or a chair. So that's what they have learned from the patterns they have already seen. Second is relationships. The model learns how concepts connect, meaning king relates to queen, man relates to a woman. So that is a gender relationship. So for learning a language, that's what is important for human, also for LLM also, that they need to understand the basic relationship. Or another example will be like Paris relates to France versus Tokyo relates to Japan. So that's the capital relationship. So it has discovered this connection just by reading the text. Third, context. So same word, different meaning. We have seen the example like apple. When somebody says, I ate an apple, that's a fruit, versus when somebody says that Apple released a new iPhone, that's a company. So the model figures out which one is based on the surrounding word. So these are the important concepts that we would need to understand for our RAG system also. So these three things, pattern, relationship, and context, are what LLMs actually understand for a language, and it does not just match the keywords. So now let's see how they use this to generate the text. So how they generate the text is pretty cool. So what they do is that they predict the word, one word at a time. So they read the context and then the next word and the next word gets predicted. So somebody says that the capital of France is, and the dash, the model is going to calculate the probabilities. So where Paris is going to have probably 95, and located maybe 2%, beautiful maybe 1%. So depending on the probability, whichever word has the highest probability, it is going to pick that. And again, going to do the same thing recursively, that again going to predict the next word and the next word. So that's how they generate the text. Under the hood, they use transformer architecture with attention mechanism. We're not going deep into that one because today's focus is the RAG workshop and not the LLM architecture, but that's what allows them to understand context even when relevant words are far apart in the sentence. And what makes them really powerful is a zero-shot learning, meaning they do not train on every task. The same model can translate languages, summarize documents, answer questions, and write code also, all without being specifically trained for each task. We know our famous models, like the examples are GPT, Claude, Llama, Gemini, Grok. We are going to use Grok in our workshop because that's like freely available, open source. So that's what we'll be using. So LLMs are very powerful. Let's see why we need RAG. What are the limitations with LLM? So the critical limitation with LLM comes hallucination. That's a big one. So LLMs can confidently generate information that sounds completely true, but it can be entirely wrong. Like for example, for the old models, when you ask what is the capital of India, it will generate, you know, the capital of India is Bombay, because probably that's the most famous cities they have seen in the pattern, but it is entirely wrong. But there is no fact checking mechanism. They will just predict what sounds right based on the pattern they have seen. So hallucination becomes a big problem. Another one, they do not have access to your private data. That seems like that cannot be a problem. You do not want to give access to your private data. That will be a security issue. But they cannot read your company informal documents, proprietary database, or your research document. Then the answer they generate, that is very, generic. It is going to be a very generic answer. So when you want to build a solution for your enterprise-based application, generic answers are not helpful. So you do want to give access to your private data or your company documents. Now, another one is the generic responses. The knowledge here is static. If you want to train your model with a new, research or new knowledge, it is going to take time. And every time the knowledge is changing so fast that you don't want to spend millions of dollars retraining your LLM model. So these are like, three important limitations. There are others also, but these are the main one which we want to solve with RAG, and RAG really helps us solve this problem. So let's see how RAG helps us. So RAG is retrieval augmented generation. Here is what it actually does. It creates a knowledge base. So it gives LLM access to your documents, your research paper, customer database, company, whatever you want. So one is that it is going to give access to your document. And again, it is not that we are giving all the documents to it, because again, then token size is going to be very big. So strategically, it has to be whatever is relevant to the prompt. That's what we are going to give. So first is that we have to retrieve the information which is relevant to our prompt. Then we augment our prompt meaning that we are going to change the prompt to say that use this information to answer this question. And then we give that to LLM. And that's how LLM is going to reason and respond. Awesome. So now, instead of LLM giving us the generic answer, we are going to have a very specific answer. So let's see the high level architecture of RAG here. So we say that, the user prompt is going to come. Maybe the user prompt is what is the vacation policy. And now we see that our RAG system, we see that one is the knowledge base. Knowledge base is a collection of all our documents. It could be 2 documents or it could be 1,000 documents. So first is the knowledge base. And we are going to see in, deep architecture that how we build our knowledge base. Second is retriever. So from our knowledge base, based on our prompt, we are going to retrieve the relevant information. So now that step is very important, that the relevant information should match with the prompt. Now, once the relevant information has come, we are going to augment our prompt. We are going to direct that you have to use this information to answer the question. And that's what we give it to LLM. And now LLM can generate the response. So voila. So now it is not, giving with the generic information. It knows the exact context it has to use to reply to this question. And now response is what you're looking for. So that's a high level architecture. Now let's go have a deep dive into our RAG architecture. And I'll give it to Ashima to give us a deep dive into RAG. Up to you, Ashima.
Thank you, Reena. I hope you guys all got the building blocks of RAG. So let's break down what actually happens inside a RAG system end to end. At a high level, RAG has 2 phases. There's an offline ingestion phase where the knowledge base is created, and then there's a query time retrieval phase plus generation where you get the answers to the query. Let's first talk about creating the knowledge base. We start with the raw data. This could be PDF files, Word files, web pages, even internal databases. And we chunk these, once we provide access to our system, we chunk these documents into meaningful units, smaller meaningful units. Each chunk is then passed into an embedding model, which converts text into a numerical representation called vector. This vector captures the semantic meanings that Rina was talking about. Remember the patterns and the context and the relationships. And these vectors now need to be stored in a vector storage. These vectors are stored, and maybe some metadata along like some source, section, timestamp are stored in a vector database, which is optimized for fast searches. The output of this whole phase is now a searchable vector index of your knowledge. Now let's talk about the second phase. This is the retrieval at query time. When a user asks a question, that query is also converted into an embedding using the same embedding model. We then perform a similarity search in the vector database to find the most relevant chunks and return the top K of these relevant chunks. The output over here is a small set of highly relevant context, not just everything. Now, in the third part of the RAG, the augmented generation part, this is when the retrieved chunks are injected into the LLM prompt. The LLM answers using this provided context, which is what grounds it in real data. And this is where you'll see things like prompt templates, context window management, and citation strategies. They become important, and all the optimization of those things happen around here. The final output is now a response that's both fluent and anchored in your source data. So we're going to go step by step in creating the knowledge base. What are the different steps? The first one was chunking. Why do we need chunking? Real world documents are too large to fit into an LLM's context window, and retrieving entire documents introduces a lot of irrelevant information and also increases cost, latency, and hallucinations. Chunking solves this by breaking down the documents into smaller, meaningful units, allowing us to retrieve only the most relevant content for the query. It improves grounding and explainability because you could get citations for the actual sources where it's getting that information from. Now let's consider this company policy document that Rina was talking about. Say it's 2000 characters. It has a lot of details that's not relevant to each query. If we partition it, say we partition it into 4 different chunks over here, 500, 500, 500, and with some 10% overlap, then somebody seeking answers on vacation policy will be able to get more precise results from that particular chunk. Each chunk is embedded and stored independently into a vector database, and at query time, we retrieve only the chunks that match the user question rather than a full document. So you have, nice retrievals, or relevant retrievals, I should say. So there are 3 key parameters to think about over here. The chunk size, which controls how much context each chunk carries. There's an overlap, which prevents loss of meaning at chunk boundaries, because if you cut it off too sharply, you could get inaccurate results. And separators, we typically want separation of chunking to happen at semantic boundaries like paragraphs and sentences rather than arbitrary cuts. And this involves trade-offs, as do all decisions. If we have very small chunks, it's very specific, highly precise, but you risk losing the broader context. If you have very large chunks, then you're back to the same problem of too much noise or irrelevant information. And medium chunks, which is a sweet spot, the production default is mostly like 500 tokens with a 10% overlap. As systems mature, teams often adopt more advanced chunking strategies like sliding windows, semantic chunking, hierarchical chunking, metadata aware chunking to improve retrieval quality. These are going to be part of our advanced RAG workshop. We are not going to cover it today. So the key takeaway here is that chunking is one of the highest impact design choices in RAG. Good chunking directly leads to good retrieval and better answers. Okay, you've chunked your data. Now we need to embed them. Why do embeddings matter? Well, numerical representations of text that capture the semantic meaning allow us to do mathematical comparisons. So we can compare these mathematical representations using distance metrics. Let's see this with an example. Each embedding actually is, vector is just an array of numbers. Like if you look at over here, a dog can be represented maybe like this vector over here, and puppy with another vector and maybe car with another vector. And if you visualize it in high dimensional space, which is what pretty much vectors do, is that they represent the text as a point in high dimensional space. You could visualize maybe the dog here, the puppy here, and the car here. As you can see, like mathematically, when you compute the distance, the dog and puppy would be close together and the car would be further apart. And if you eyeball the numbers over here, you can see what I mean. You know, dog and puppy seems to be closer in numbers, whereas the car is far apart. Okay, so we basically now know that embeddings are basically numerical representations of text. And if they are similar meanings, they are nearby points. If they are different meanings, they are far apart. So semantic similarity search is basically enabled using this distance metrics between vectors. Some of the key parameters that matter in the embeddings is first is the embedding model. The model determines how well the semantic meaning is captured. Some models are general purpose, mostly for our purposes, we could use those. Some are domain specific because you really want to fine tune it for a specific domain, multilingual or multimodal. And stronger models usually improve retrieval quality, but they come with higher cost and latency. The next one is vector dimensionality. Dimensionality controls how expressive the embeddings are. Higher dimensions can encode more nuance, but then they increase storage requirements and they also increase the search compute time. And then there's the max input token limit. This is a constraint on that influences the chunking strategy. It's like an upper bound on the chunk size. And finally, we have the normalization behavior, which is, some embedding models return normalized vectors, in which case you want to use the cosine similarity as a distance metric versus unnormalized vectors where you would use the dot product. So when you choose the embedding model, you have to also figure out what distance metric would be best used with that. So some common production pitfalls are using the similarity metric that doesn't match the embedding model, we just talked about it, or increasing vector dimensions without changing the model, and expecting better results, or treating embeddings as static even when the data or the models change. Embeddings form the semantic foundations of your RAG system. If embeddings are weak or mismatched or poorly configured, retrieval quality will suffer, no matter how good the prompts or the LLM is. So now chunking defines what gets embedded and embeddings define how meaning is represented. Search will define how relevance is measured. Okay, so the next step after doing chunking and embedding is now to store the embeddings in a vector database. But before we get there, we're going to take a small detour to understand how searches work and why we need vector stores. The simplest approach to do a vector search is using k-nearest neighbor. So if you look at this picture on the right, you can visualize maybe that each of the document chunk that you embedded is this blue dot. It's a dot in a point in high dimensional space. Now you have a query vector coming, which you can think of as this orange point. If in the KNN approach, the distance is computed between the query vector and each of these document chunks. And then after the distances are computed, we sort the results and return the top k closest matches. As you can see, this is a very expensive operation. Scales linearly with the number of vectors, and the number of distance computations is pretty much equal to the number of document chunks. So if you have thousands of millions of chunks, there's going to be really high compute cost and latency. There are some indexes that help to make this search faster. For example, in the inverted file index, which vector databases use, you could cluster some of these document chunks. You can use a clustering algorithm and cluster them, compute the centroid, which is the average of these clusters, and then that will act as an index for searching. It really improves the search speed, but those are part of kind of already included in vector databases, which is one reason why we need them. We're going to talk about another approach that really speeds up the search in vector databases. This is called approximate nearest neighbor retrieval, and it's based on using navigable small world graphs. And I'm just going to give you a small example of how this works. When a query comes in, we don't compare it against every vector in the database. That would be very slow, as we just talked about. Instead, there is this proximity graph that gets created where each document chunk is connected to its closest neighbors. So it kind of creates this web-like structure. So now imagine this query point come in, and we start with a random document chunk point, and we compute the shortest distance, not the shortest, but the distances from this document chunk to the query point and of all its neighbors as well. And we find the smallest one. In this case, it would be this one. Then we start computing the distances of its neighbors to the query point. And we stop the process once we find that there is no other shortest distance to be found. In this case, this one is pretty much the shortest comparing to this or this. And so we can see over here that each hop narrows the search space. So we are examining dozens of vectors instead of millions. And that is why this is called an approximate nearest neighbor search. We trade a tiny amount of accuracy for massive speed gains. Because, it really depends. We might have something else down here, which is not a neighbor of that. But we kind of stopped here. But still, it gives you very good results. Now, you can think of another approach that betters this. There are many actually approaches that kind of build upon this. One of them is called the hierarchical navigable small world, and in this case each document connects again to its nearest neighbors, but we kind of form a hierarchy among it. It improves the NSW graphs by adding the hierarchy multiple layers to the graph. The top layer has very few vectors. So if you have like the bottom layer have 1,000 vectors, then this layer would have probably 100, and then this one maybe have 10. And we start the search at the topmost layer, which is a kind of a coarse search. So you find this, the closest vector over here, and dig down. Then you find the closest vector there, and then dig down further. So you can see there's multiple graph layers, and the top layers have fewer vectors. So it's a coarse search. The lower layers refine that search, and it achieves near logarithmic search time, which is really, really fast. Now, why do vector databases matter? All of this logic, this graph construction, hierarchy, fast navigation, it's handled by vector databases. A vector database stores the high dimensional embeddings, builds these proximity graphs ahead of time, and exposes fast ANN through simple APIs. Without this, semantic search and RAG systems would be too slow and expensive to run at scale. Okay, you've done chunking and embedding, and you've understood why we need vector databases. We're going to just go over vector databases in this slide now. Once we generate embeddings, we need a system that can store these millions of vectors and retrieve it fast and quickly and reliably. Now, vector databases, along with implementing, similarity searches so fast, they also optimize storage by doing techniques like quantization or sharding. We were not going to get into those parts today. Vector databases are specifically built for the purpose of fast retrievals. They support scalable indexing and low latency similarity searches. Traditional databases are not really optimized for this kind of high dimensional nearest neighbor search. How do they work? In a typical RAG system, we store one vector per chunk along with the metadata. The metadata might include things like document IDs, sections, timestamps, authors, etc., etc. And at query time, the user's question is converted into an embedding using the same model. And the vector database then performs a nearest neighbor search using a similarity metric to find the most relevant vectors, and associated text chunks are returned and passed to the LLM for generation. Some of the key parameters and trade-offs involved here are index type, which controls how vectors are organized. We talked about the inverted file index, we talked about HNSW, and there's others like flat indexes or compressed indexes that trade off speed, accuracy, and memory usage. Then there's the metadata schema, which determines how rich or flexible filtering can be. Rich schemas improve precision but add complexity. Index build and update strategy, because you might have more data come in. Your knowledge bases may not be static, they may be getting updated. This affects data freshness versus efficiency. If you're doing batch indexing, which is pretty efficient, but is less fresh, while streaming updates provide real-time data, but at higher cost. And then scalability and deployment choices, managed versus self-hosted. You want to trade operational simplicity for control and cost. So across all of these, the trade-offs are speed, scale, flexibility, resource usage. Some of the vector databases commonly used are listed down here. I'm not going to go through the pros and cons of each one of those. But for our purposes in this workshop, we will use ChromaDB, which is lightweight and open source, perfect for proof of concept workshops like this one. So we've gone through chunking, which is breaking the documents into smaller manageable pieces. The tool you are going to use in this workshop is recursive character text splitter. Then embedding those chunks into numerical vectors. The model you're going to use is sentence transformers. It's open source, no payment required. And vector storage is finally storing those embeddings into vector storage. We just talked about it. We're going to use ChromaDB. And now you're going to build this with Rina.
Awesome. Thank you, Ashima. That was actually a deep dive. Let me share my screen. I hope everybody now can see my screen, and I'm sharing Google Colab and RAG workshop. So we are going to build now the whatever we have learned so far, the chunking, embeddings, and then the vector store. So I believe everybody has that open. We are going to share the code in the chat. So please, if you have not opened your Google Colab, please open it now, and we are going to start coding now. So let's get started. So for the step 1, and if you have not from the file, go open a new file. You can open a new notebook and get started. If you're not familiar with Google Colab, run all is going to run all the code. But since we are, writing the code in the blocks, this is how we are going to run cell. So let's see what we are doing here now. So again,
Yeah, sorry to interrupt. Just one second. Just everyone can give a thumbs up that they have their collab open and they can run it when Ashima puts stuff in the chat. We'll do it one by one so that you can see what Rina is doing on your end as well.
Awesome.
Thank you.
So I hope everybody has the Colab now open, and let's get started. So for this one, what we are doing is that PIP is Python install packages, and this exclamation mean that do not run this as a Python code, but run this as a shell command. So now we are going to install the packages. LangChain, that's a RAG framework we are going to use. LangChain community, we are installing the package. That's the third-party integrations. So we do not have to write everything from scratch. We are going to use a lot of external third-party packages. LangChain text splitter that we are going to use for chunking. Sentence transformers for embedding. ChromaDB for our vector databases. Hugging Face again for embedding. And then we are using Grok. So we are installing our package, and we have a last print statement, install it complete. So I hope everybody has done the first step. And the code is there in the chat. So let's move to the next step now. I hope everybody has gotten the first step right, because every step is going to be important. Make sure first step is done, installation complete. We have Gemini also here. If something is problem, please either write in the chat or say that, you can ask the Gemini also, but hopefully whatever is being shared, that should work without any issue. And remember to run your code. So second one is first step. We did all the installation of the packages. Now we are going to import the libraries which we are going to use. We said the package text splitter for the chunking. So recursive text splitter is the one we are going to use for chunking. Hugging embeddings, Chroma for vector DB, and then for documents that we are going to use. So that's the second step. We are importing all the libraries we need. So we have not done anything extra right now. We are just setting up our system that what all libraries and packages we need. third step is that we are going to keep it simple. We are not uploading any complex document right now. We are going to upload, we are going to do first track exercise with very simple documents and only the text document. So
Yeah, one sec. I think
yeah.
they are saying they're not able to, somebody saying they're not able to see the chat. So you
Oh, they
cannot
are
see
not able
chat.
to see the chat. Okay.
Yeah, so I just want to make sure because you're
No, I think we are able to see the chat, but it is disabled for us to reply back on the group chat.
okay. That's okay. That's for purpose because we didn't want
Okay.
the
Sounds good.
instructions and the things to get mixed up. So
Okay.
if you have any questions or anything, you can send it to me. You can send it to Ashima or Reena. Just
Okay.
send it my way because I'm keeping track of all the questions and I will ask them in the end. And any troubleshooting stuff that you have, I will help in that as well. Anita, you had something you're asking about a file. There's no file. There were like steps that we had. Yeah. So yeah, just
Yeah,
keep
that
copy
is right.
pasting it.
So yeah,
Yes,
I
yes, absolutely.
followed the step one. Yeah. And
Okay, perfect.
okay.
If you want us to wait, please feel free to unmute yourself and say, just hold on, we are still doing it. We are happy, more than happy to slow it down and go at everyone's paces. But just unmute.
So yeah,
No, it's
Sangeeta.
not a common collab actually. It's you can create your own Google collab, right? And your own Grok key. So I'm answering Mala. I think that's your name, if I got it right. Or maybe I'm saying a short form of.
I have a question, Sangeeta.
You
So
can
I
call me Mala.
completed.
Yeah, I was able to open my own collab.
Okay, thanks, Wiz.
Yeah.
Yeah, sorry, you have a question, Anita? Go ahead.
So I copy pasted the code for the step one, and I think I got some error message which I pinged you, Sangeeta. Is it common? But towards the end, it mentioned installation complete, though. I'm not
That
sure.
should be okay because there are some warning messages. There sometimes a
Oh,
message.
yeah.
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 So if you got
Yeah, that's fine.
installation complete and some warning messages, that should be okay.
Okay. Actually, it was an error message.
So it was an error message.
Yes.
Hang on. Actually, I got an error message saying its pip dependency resolver does not
Exactly.
currently take into account all packages, blah, blah,
Can
blah,
you
blah.
try the second step if importing the libraries is working? Maybe those were just the warning messages. Sometimes it gives you because there are like different dependencies which are not going to be part of the which should not matter in running our code. Sometimes there is a dependency conflict, but
Usually means you already have something installed in lieu
yeah.
of it, so that might still work.
So if you're able to do the second step, import libraries that successfully, then hopefully that shouldn't matter your warnings.
So step 3 also, we are pasting it as a code, as a new code text box.
Yes. So for the document, step 3, the Google Doc is shared. So from there, you can just take the documents because for the simplicity, we are not uploading any documents because people will have different documents. We just want to first finish, how the different modules work. Next exercise, we can do on the uploading a different documents, which you can try.
Yeah, and sounds good. And step 3 is essentially within the code, we are just defining this documents array.
Yes.
That's correct.
Yes.
That's
Yeah.
correct.
Yes.
That's correct. Because it's a big document and we cannot paste it in the chat. So
Yeah.
that's why we're giving a link for that one. Yes, yes.
So do we actually paste that step 3 thing?
Yes, you actually
Yes.
paste that as step 3 and then just run it.
So you
Oh,
get
yeah,
you have to get the document from the link and then just copy paste whatever is in that link you see and put it in step 3 in your Colab notebook.
Oh, okay.
Yeah. So go to the link, copy paste what's there, and put it in your cell in your third or fourth cell that you have over there.
I believe people were asking questions about the documents. That means first two steps are done now. And third one is about the documents. So here we are just defining our documents. Here I have 4 documents. It's an array of 4 documents, simple text documents here. And towards the end, we are just printing the length of the documents and the characters. That's what we are going to print. So once you have defined, copy pasted, remember to run this code and it should print that, the 4 policies, how many characters are there, and documents length.
Yeah, if everyone can give us a thumbs up if they've completed the step 4, so then that would be great.
Yeah, that would be awesome.
Step 3, right? Is that
Step 4. There's step 4 as well, like
Step 4 we have not yet shared. So
Oh,
that was
I mean
step
step 3, and then after that, step 3, Ashima
And
pasted
then the
another
print.
code,
Yeah. And then the print.
so
Okay.
yeah, and the print command. So if you can do till that point and give us a thumbs up, then we know
Awesome.
everyone has caught up.
So let's talk about the step 4
three-
now.
Just wait, just everyone give a thumbs up and then.
Okay.
So with step 3, are we supposed to get any response when we run
Yes,
it?
so after step 3, Ashima has actually added another print command. So if you do that as well, like Rina just showcased, right? It will show you the document length, policy 1, policy 2, policy 3, policy 4, number of characters. So if you reach till that point, just give us a thumb.
Okay, so I have not got that response. When I run it, nothing happens actually.
Can
Did
you
you
check
paste
if the printf documents, the printf is there, like if you can see my screen here. So what we have is the document array. So 4 document array, and there is a closing brace, and then the printfs. So do you have exactly like similar thing?
Yeah, that is correct. I copied it from the document.
And
Okay.
then I added the printfs after that. If you check the chat, so you have to add.
Okay. Sorry, got it
No
now.
worries.
So, mhm.
So
I'll wait
everyone
for the
has a
thumbs up for the documents, and then we'll go to the next step.
I saw from Arav and Yem.
Okay, I see number of
I
thumbs up.
think. Okay, yeah, I think we can go.
Awesome. Thank you. So the documents are there, and we can see that the number of characters loaded 4 documents. So we know that these are the documents we are going to work. So now first step, chunking. Chunking meaning that we want to split this document into smaller pieces. And as Ashima shared in her slides, that we want to split it because we want to make sure that when we are giving the context, one is the token size is reduced, and second is we are giving the right context. Otherwise, if we give too much of information, again, it might hallucinate. So recursive text splitter, which we imported earlier. Chunk size 500, meaning that the chunk size should be max 500. Overlap 50, so that we can see that how much overlap is happening. Separators are, document is very simple. It's a text document. So simple separators, new lines, single line, double line, or comma or dot. But if you have a multi-model document, we are not covering multi-model in this RAG workshop, this one. Maybe that will be part of the advanced RAG, but then your separators will be different, your chunk size will be different. So separators are going to be more complex. And now here, I have defined my function, how we are going to split, and the documents are here. So text splitter, that was the function. Now I said split documents and these docs and the chunks. So these are the chunks where I have now split it into 500 characters max. And so currently, again, we have not done anything about RAG. We are just splitting our text document into chunks. So let's see. Remember to run it, and we should see the chunking results. And it should say that there were 4 documents, but it created 86 chunks. Depending on the splitters, depending on the max character size. So one chunk was 330 character, another one 424. So there will be different sizes depending on the separators.
So one
I'll
question.
wait for a thumbs up again for chunking that everybody has done. So people should see that the chunks are there now available, and we are doing some printing that the chunks are available now.
So one question. You said, typically the chunking medium is 500 tokens. So I'm assuming 500 tokens comprises of almost like approximately 500 words. Is that right?
500 characters.
Oh, it's 500 characters.
Yes.
I see.
Yeah. Also,
Yeah, go ahead.
Also, I wanted to say that it's like Veena mentioned, 500 is the max. The recursive text splitter, it splits on boundaries. So it tries to split on paragraph, sentence boundaries. And only when a paragraph maybe exceeds 500, then it'll kind of chop it, right? Depending on where it thinks is the right spot to chop, which is why you see somewhere you see 360, somewhere you see 425, right?
Yeah. So let's say if we are building a vector database for, let's say, documents, that an average size of documents is, let's say, 10 gigabytes to 20 gigabytes,
Mhm.
right?
Mhm.
Even in that, we would still stick with the 500 tokens as the chunking size, or would we use some other criteria to come up with the chunking size?
So, you know, a lot of RAG systems go through fine tuning. We are not going to go through a lot of detailed fine tuning in this exercise today, but you could try with, Rina could show you, we could try with different chunk sizes, right? You can try with 1,000 or 2,000 and see how your retrieval, performs in terms of latency, in terms of accuracy, in terms of precision, recall, all these different metrics. And then you go back and fine tune it and maybe come up with a sweet spot of what works for you, right? In term, and you can measure those metrics like latency, cost, performance, accuracy.
I'm just going to add to Ashima's comment there. It actually also depends upon, what your document has, right? How your document is organized, what information it has. So you might have considered that into place as well.
That
Right.
is
So
true. For example, if you have a document that has like meeting transcripts, for example, then you don't want to just break it randomly. You might want to break it by speaker, or you might want to like not break it at all because there's a loss of context. So
Okay.
yeah, it depends on what kind of documents.
Okay. Thank you.
yeah, plus it will probably not depend on the length of the document. It is how the context will be that, because like whatever length of the document does not matter, because you may chunk your 100 documents or 2 documents. It will depend that how the context is part of your documents. So that's where it becomes important rather than the length of the document.
Okay.
Awesome.
Mala had the same question. I think we answered that for her. Thank you. Mala
Thank
Arvidsky.
you. So chunking is done, and now comes the embeddings. Embeddings meaning whatever chunk we have done, we are going to give a mathematical representation to that. Because LLM does not work on the text, because it will be hard to match that whether you are looking for a holiday policy or a vacation policy. So it is not going to match with the keywords, but it is going to work on the vectors. So this is an important part. We are using Hugging Face embedding, and the model name is here. That's the model name we are using. And now again, that depends that the chunk and the embeddings, that becomes like which model you are using. Based on that, your vector will be created. You have a better model, your vector dimensions will be better, and your similarity search or different search will be better. Older models may not have that many dimensions. So the model we are using here has 384 dimensions. So Hugging Face embeddings, this is the embedding we are going to use. And when I say embed a query, I'm not yet embedding our chunks. We are just embedding a test query. What is the remote work policy? And then sample embeddings is going to say that, how the embedding is working. So when we say length of the sample embeddings, it is going to say that how the metric dimension is. And then the sample embeddings, I'm printing first 30 dimensions. You can print all 384 or less. You can try with that. When I run it here, you can see that embedding dimensions are 384. And this is how the embedding got created. So this is to see that what exactly embedding means, what the vector database vectors mean, not vector database, what the vector means. And this is for this query, not for our chunks. So I'll wait for everybody to finish this step.
So how is the 384 dimensions relevant or significant to the data that we are trying to store in the vector database?
Yes, so see, the more the dimension, now the newer model actually has the 500 dimension also. So more the dimension meaning it has more context or the more relationship about your chunk or your query. So depending on how how your embeddings are created, they will have more information, more context, and you will have better answer. So
So
that's how
just
you
to, yeah, Reena, just to add to what you said. So if you look at, some of the examples Reena had given before, right? Bank, now bank can be like a river bank, or it can be like a financial institution, or it could be like, and then is it a small size bank, mid size bank? And then does it offer loans? There's so many parameters that go when you think of a bank, right? Does it have a safety deposit? I mean, there could be so many parameters. So dimensions you can think of as parameters related to that word, okay? And not, and they capture the context and the relationships and all of that. But then even context and relationships, there can be many parameters that define that. So if you have more dimensions, you can capture more of it. If you have less dimensions, you capture less of it. So if you have more dimensions, then you are probably getting more accurate answers. But sometimes you have to balance whether it's worth the cost. Does your application require that much of accuracy or not? Because if you have really large dimensions, then the cost goes up.
Okay. So now let's say if my data set has multiple languages, right? Let's say the data set could be Indian, Chinese, English, Chinese, and some Indian language. So then does that mean my dimensions, the embedding dimensions will increase?
Those things will not directly increase your dimensions because that will depend on the model, the LLM you are using. If it has a translation capability, it will be able to translate it also. So embeddings are going to maintain the context, but your language transfer capability will depend on the model you are using also.
Okay.
I hope that answers your question.
Yeah. So essentially, if like irrespective if anything in English words will be within the proximity of rest of the English words. Anything in another, let's say Chinese language, will be in the close proximity of Chinese words. And that's how when we try to retrieve, it will, it will look at the proximity and it will probably retrieve back, I'm guessing.
Yes, I think it will depend. So I think I may
So
not have the correct answer for different languages. Maybe I'll let Ashima answer this one.
yeah, so I mean, for multilingual embeddings, like they have multilingual models, like I know
Yeah.
there's like Embert and things that have a shared embedding space. So in the shared embedding space, semantically, just like what you said, semantically similar content in different languages will map to nearby vectors. So it doesn't necessarily have to be like large embedding.
Okay. Thank you.
Another thing is for multi languages, these days what I'm seeing is that companies are not creating multilingual documents. I mean, they have document in English, and then whatever if the language is in say comes in some other language, they first translate into equivalent English, then get it the relevant thing, and then translate into the language. So that's the route I've taken and seen them taking as well.
I believe everybody is sorry, you are saying something here?
No, please go ahead. Yeah.
Okay. So everybody probably has done the embeddings. You can again experiment. You can print all the 384 dimensions or 30 or 10, whichever you want, or you can try with a different query that how the similar words will have similar metric versus a different one will have a totally different dimensions. But it will be hard to make out just by looking at the numbers. Let's see. Let's go to the next step now. We need to create the vector store. So Chroma was the one we said, we are going to use. And now we are going to say that. So previously we have defined our chunks and we defined our embedding functions. We didn't embed yet our chunks. We were saying that embeddings is our method, the way the embedding should happen. So Chroma, when I say from documents, I give my chunks, I give the embeddings, how the embedding should happen, and the collection name, company policies. And this vector store should be the one which stores the vector, is going to be my vector database, which has all the chunks in the embeddings form in the vector database. And I just printed a vector store. This was not supposed to print everything. It was like an object. So it is just to say that yes, vector store got created. It is not undefined or null. So that's what we did, that there were 86 chunks. So 86 documents we are storing in our database. So vector store done. And now Ashima did talk about a little bit about the similarity search. And now let's see if we can retrieve the information from our vector store. I believe everybody is done with the sixth step, that the vector store got created. And now we want to try that can we retrieve information from our vector store. So here the stored count, we are just printing that what was the vector store. And this is the where we are doing the similarity search. And I'm again not doing any further question. It is a very simple word conference. And k equal to 1, maybe we'll talk this about in the next slides also and next exercise when we continue. But k equal to 1 for now, that we just want a one first resource, that how many resources we can fetch. So k equal to 1 gives that I just want one similar document, relevant document. So sample, when I print that the sample chunk, it gave me one chunk. So 86 were in the database and all chunks stored successfully, and we got the first chunk. So this was our first sample with the similarity search. Let's try another example for a similarity search, and then we'll go back to Ashima for the further deep dive in the RAG system. So we have not done RAG yet. We are just creating our knowledge base, and we are seeing that how to do the similarity search or how to retrieve the documents. So we have not yet built the complete RAG system. We are just building our knowledge base, and we are saying that how we retrieve the document. So this time I'm doing a query. How do I plan remote work? And k equal to 2 when we give to vector store, that means I want two relevant documents and the relevant documents, and I want to just print them, that what it is going to print. So for this query, two relevant documents, we got that remote work schedule or the communication requirements. So we will see more details. I'll give it back to Ashima and continue our deep dive into RAG, and we'll come back to exercise. Thank you.
Okay, guys. You guys have done chunking, embedding, and storing into the vector store. So we've finished our knowledge base creation. This is done. So let's move on and talk about retrieval techniques. Up to this point, we've stored embeddings in the vector database. Creation of the knowledge base is now complete. Now a user asks a question. The system's next job is to figure out what stored content is relevant to that query. Search is the mechanism that connects the user's query to the stored vectors. It compares the query against the vector database and ranks results by relevance. There's two main techniques that are commonly used. One is the keyword search, which focuses on exact word matches. It works well for precise identifiers like error codes or inventory SKUs. And then there is the semantic search, which works better for natural language questions because it focuses on comparing the meaning. Most production RAG systems will combine both because semantic search gives you high recall, and we'll talk about high recall, what high recall is in a bit. And keyword search gives you high precision. So we combine both to get the best of both worlds. And we could use some filtering as well, and we're going to talk about that metadata filtering as well. So vector databases store meaning, and search determines which meaning matters to a given query. Now, when we talk about keyword searching, let's delve a little bit into how does this keyword search work and why does it even matter. So sometimes users just care about exact words. So for example, if your refrigerator threw an error code like ERR 502 or something, you want to basically search for just exact that error code. Or if you sure you like a certain kind of protein bar and you go to the Walmart site and say, I want pure protein bar, chocolate peanut caramel, 20 grams protein, gluten free. I don't want to look at the whole set of products you've got. I just want that. That time keyword search becomes extremely powerful. It guarantees literal matches. It's fast and it's transparent and there's explainable, scoring. So how does this keyword search matter? So imagine I have this query, how to bake a spinach lasagna. And there's a bunch of documents in my document base. In each document, for each of the term in the query, we give it an importance score. We calculate an importance score. This importance is measured as, it's a product of term frequency and inverse document frequency. I'm going to talk about this a little bit more. Term frequency answers how much does this document talk about this word. A word appearing many times contributes more to the score. So it's kind of also normalized by document length, because there could be a lengthy document with the same word appearing many times but not really adding more value. So you kind of do some normalization around it. Inverse document frequency what it does is, it basically, you can think of it as that not all words are created equal. Words like, for example, how or to will appear in pretty much all the documents, whereas words like lasagna or spinach may only appear in a few documents. So we want to penalize common words and reward rare informative words. So IDF is computed as like, you can take the ratio of total documents divided by documents containing the term, which is why it's called inverse, because the actual ratio is documents containing the term over total documents. And then usually we take a log of it for, again, normalization. The final score is TF into IDF. This is what defines the importance of this term in this document. Now, when we have the importances of all the terms, we get a total, we add up all of this, and that's the total score. And the documents with the highest total score are returned in a keyword search. So, what is the flow? You can say the user prompt comes into the retriever, and that creates a sparse vector. This is what we call a sparse vector for that prompt, and then it finds the relevant documents. Another approach is called best match 25, which is just kind of like an upgrade, like a plus plus on of the TF IDF thing. It does some length normalization and some saturation and things like that. 25 stands for the 25th iteration. So there are multiple iterations trying to better the previous one. So we won't get into much details, but the engine is still the same. So this is how keyword search kind of works. Next, we're going to talk about semantic similarity search, and you've already seen a flavor of this. You've done some work as well now, but let's see a little bit more details. Now that we've stored meanings in vectors, so those are called dense vectors when we do the embeddings. This semantic similarity search is how we retrieve that meaning. So a user comes up and asks a question: how do I reset my password? The challenge is that users rarely use the exact same wording as the source document. So keyword matching is not really going to be enough. And we want to retrieve content based on meaning. So what do? We convert the user's query into an embedding vector using the same embedding model. And then we kind of compare it to the stored vectors. To find the closest vector in the stored vectors. What do we mean by the term closest? Closest is defined mathematically by various different distance metrics like cosine similarity, which measures the angle between the vectors. We talked about how it's best for normalized embeddings, or Euclidean distance, which kind of measures it's kind of like the Pythagoras theorem. It is sensitive to magnitude, or dot product, which measures a projection. It's good for unnormalized vectors. So there are different distance metrics, and we compute those, and closeness is measured in terms of this. Now the key parameter over here is k, like you just saw Reena talked about. K equal to 1 is what you had in the workshop. K is the number of similar documents to retrieve. Typically it can be anywhere from 3 to 10. In the example that we see over here, it's 3, like the top 3 most similar documents are returned. Now you'll also see a score over here. It's called the similarity score, And so there is an optional parameter on score threshold. You can choose to filter out, say, results which are, less than 0.8. So then you only get results that are above 0.8, and then the K is applied to those results. So semantic similarity search determines which pieces of knowledge the LLM gets to reason over, which is very important because the LLM is going to use that. Now, I also wanted to talk a little bit about metadata filtering. Why is it important? Metadata filtering is not about relevance. It's about eligibility. It ensures that we never retrieve documents that the user should not see or doesn't care about. So it ensures compliance, permissions, freshness. It's commonly used to enforce control or filter by ownership, or limit results to paid or premium content. And how does it work? It can be applied, the metadata filtering can be applied either before or after retrieval, or in both places. So common metadata fields are like author, timestamp, access privileges. And the documents have to pass all the filter conditions to be eligible for the retrieval. There is no scoring or ranking. It's just a binary pass or fail. So you can imagine that these are very fast and highly optimized because they're deterministic. They are also reliable, easy to understand and debug, and really good for ensuring security and governance. In best practice, real systems metadata filtering is almost always combined with keyword and semantic searches for both safety and relevance. And now you're going to basically do some similarity searching with Reena in the workshop. Back to you, Reena.
Thank you, Ashima. So we are back to our exercise again. I hope everybody can see the right screen again. So let's get started. So just to again give a recap what we had done earlier, we created our chunks, we created our embeddings, and then we created our vector store, and we did some similarity search with some queries. Now, this is a time to see that how our RAG system is going to work. So we are going to now set up first our LLM. So far, we have not set up our LLM yet. I hope everybody is able to see my screen, right? Okay. So now set up the LLM. We said we are going to use the Grok, and we would need the Grok key. And from the document we did say that it is good to keep your Grok key in the secrets. That's what I have done here, and I'm going to use userdata.get for the Grok key. If you have not put that in the secrets, that is fine. You can just hard code that key here, because I'm presenting, that's why my key is hidden. But since you're not sharing yet with anybody, you can put it as hard coded also. Chat Grok we are using, and then the model number and the Grok key we are giving. And again, here we just want to make sure that we can invoke our LLM. I ask how many days can I work remotely, and we give LLM.invoke and the question, and I'm going to run this code. So my LLM has been set up. Again, we have not done the RAG specific questions. It is a very generic. So we are just setting up our LLM to ask questions. And here the answer for the how we can work remotely, that's a very generic answer it gave. I wait for the thumbs up that everybody has set up their LLM. Let's go to the next step now then, and that's defining the RAG function. That's a very important function. So let's see what we are doing here. So far we created our vector store, our LLM. So now I'm defining a RAG. Ask RAG is my definition for the function, and it is going to take the question we gave, the vector store, the LLM, which we did set up just now, and then k equal to 2 by default, but we can say that how many relevant document you want. And what this function does is, from the vector store, it is going to make a similarity search with that question. That means it is going to fetch the relevant document. So if you remember the high-level document, we had the knowledge base, and then with the prompt, we wanted the relevant documents. Now, I combine all those documents here in the context, and then the prompt, we say, answer the question based on the following context. And here I specifically say based on only on the following context, and I provide the context and give the question. So again, for the workshop, that only works because we are not looking for the generic information. It is not a research paper, but if you're working on a research paper or your company document where you want to compare, say, the real market also and your company documents, only is not going to work. The augmentation of the prompt is going to be more complex. So depending on your multi-model, whether you need the images from outside world also, from your document also. So augmenting the prompt is also like an art, but here for the simplicity, it is just that use this context. And here then we invoke our LLM with the prompt and answer the question. It did nothing because we are just setting up the definition. I'll wait for everybody to finish this step.
I think Anita had a question in the meantime.
Yeah.
Go ahead. Yeah. Or maybe it was an accident. She wanted to do thumbs up. Okay, never mind.
Okay.
Oh, I'm sorry. I think I was speaking with the mute on. So here's a question. So yeah, step 9. I understand that this is querying only the LLM, like is it chat, Grok, I think, and without the vector store that we created, right? And the step 10 is assigning the LLM with the vector store. Is that right?
Yes.
Okay.
Yes.
Okay, thanks.
So this was just setting up our LLM that we can invoke. So it is just instance of LLM, and we just wanted to test that LLM is working. So we tried LLM dot invoke with the test query. And here we again have just defined our RAG function. We have not yet used it.
Okay. Yeah, thanks.
I believe everybody is done with the number 10 steps also. And now we are going to see the next step, the RAG. I think the numbering is wrong. This should have been the 11, but this got the 10. Okay, so now the question, I think people are really waiting, how many days can we work remotely with the, how we have defined in our document. Now I'm invoking the ask_RAG function with this question, and then we provide the vector store. This is the same vector store we created. So this is now not the generic like a function I'm defining. I'm actually providing my vector store that use this one, the LLM instance, and then here I'm saying I want answer based on 2 relevant documents. So here we are going to print the result from the answer and then see how many relevant documents it fetched, and it should have 2 relevant documents. Awesome. So this is our first RAG based answer. Now how we can work remotely is based on our documents. It says we can work 3 days per week rather than a very generic answer which we saw in our LLM that, oh, it is going to give a general guideline how to work remotely, but not based on our document. So now the answer, when we say with ask_RAG, these are very specific answers based on our documents. I'll wait everybody to finish this step. Awesome. I believe most people are done with the first RAG question. This is nice. Let's try another question. And from our document also, the one of the HR policy was about the health benefits. And now we want to try that if we try the 3 relevant documents and then how the answer is going to look like, then ask_RAG again, we invoke with the question and everything same. And now it gives us 3 documents that it found, and the health benefits include these. Awesome. So first RAG exercise, the basic one is done. We have experimented with chunking, embedding, vector store, then LLM, and everything is modularized in such a way that you can replace it with any model, whatever you want. You can replace it with any other vector store also. So you can experiment with that. But before that, we are going to talk, I'm going to give it back to Ashima, because so far we have seen the RAG responses, but we want to make sure that we understand how to measure the quality of these responses. So we will go back to Ashima. We'll stop sharing and let's go back to presentation.
So one question.
Yeah.
In that step 10, like, you're giving question and then you're doing an answer LLM invoke of the prompt, right?
Yeah. Yes.
And after you invoke the LLM is when you make the RAG call? Why? No?
Yes. So what we have done here, I'm sharing back my screen. Hope everybody can see it. So this is the prompt where we have augmented our prompt to say that I'm going to provide the context. Context is my set of relevant documents which I retrieved from here. So this context has that, and I'm saying that answer the question based on the following context. So it understands that the context is there, the question is there, and it has to give the answer in this format. And when generating the answer, it is going to invoke LLM with this prompt now.
So I think what Reena is trying to say is that we have changed the prompt with the ask_RAG. Now the prompt includes the context that you fetched from your vector database using the retrieval. So it's already, the prompt itself has changed. So now when you invoke the LLM, it has a changed prompt.
Okay. Okay.
So here we, in the previous one, when we just raw invoke, we just gave the answer question that how many days can I work remotely, and then it gave the generic answer. But here we are giving the context information, and the difference is instead of providing all the context, because my HR policies may be 10 documents or maybe 100 documents on different topics. So I'm not providing all the 100 document and say that now the token size is big and LLM has to go through all the documents, but it had done a very intelligent search for the relevant documents first, and that's what we give to generate a good answer.
Dina, maybe if you could print like the prompt after, after it, before it invokes before it's passed to the LLM invoke, if you can just print it.
This one?
Yeah, before it.
Yes, this is the prompt here. So, sorry, what should I do?
Now I was just saying, can we print the prompt?
Oh, can
Yeah,
we print the prompt?
just before the answer is equal to
The
LLM.
augmented prompt, so that they can
Yeah.
see that the prompt has changed.
Sounds good. Let's go back to the PowerPoint, and meantime I'll change so that we can see the actual prompt, and we'll see that in the next time we come back to the exercise. Does that sound right?
Yeah, sounds
That
good.
sounds great. Thanks.
Sounds good.
Okay, everybody can see my screen? The presentation?
Yes.
Okay, great. So before we go to evals, I wanted to talk about how, I said that most production RAG systems, both use semantic and keyword search. So we're just going to go over that a little bit. So far, we've covered chunking, which is what text units exist, and embeddings, which is how meaning is encoded. Vector DB is where meaning is stored, and search is how meaning is retrieved. Now, in this slide, we're going to show how keyword search and semantic search work together in real production RAG systems, and where metadata filtering fits in. Usually, there's like parallel retrieval paths. So one for keyword search and one for semantic vector search, and these two retrieval paths run in parallel. The keyword search, as we talked about, retrieves chunks from exact term matches, and it's very strong for error codes, product names, legal or healthcare terminology. It has very high precision, but it has limited recall values. And semantic search, on the other hand, uses embeddings to retrieve chunks based on meanings, and it finds highly relevant content, even with when wording may differ, and has a really high recall. So metadata filtering can happen before the retrieval happens. And this can be, before retrieval is when you have hard requirements on what defines a legitimate search boundary. For example, it's like permission-based accesses, and employee searches a company knowledge base, and you want to make sure that they are only searching in a search space that they're allowed to. It saves computation, it prevents unauthorized exposure, and it eliminates irrelevant scope entirely. After retrieval, which is post-filtering, you may want to refine already relevant results based on secondary soft criteria. Like if you want to say, I want relevant results, beyond a certain time, after 2025-0101. So in that case, what happens is that you still get highly relevant results, and then you can choose whether you want to really filter out some of those or not. But you don't automatically just filter out results which could be important. So that's where both kind of metadata filtering, both before and after retrieval, can happen. So the key difference is hard requirements, you do it before, which eliminates the search space, and soft preferences like refining of the relevant results can happen after retrieval. So now we've kind of, at the parallel retrieval stage, we've kind of gotten a set of lists, say 20 to 50 retrieved documents from each of these searches. And we now have to combine them into a single list before we choose certain top K documents from this to send for prompt augmentation. So to combine them also, we have to use a specific function, and there are many functions to do this combination. One of the function is reciprocal rank fusion, which we're going to talk about. This ignores the raw similarity scores we saw in semantic retrieval. It just looks at the rank position. So for example, document A is ranked 1 in this one, document B is ranked 2, and document B is ranked 1 over here, and D is ranked 2. So it only looks at the rank positions, and documents that are ranked highly in both the lists get rewarded. So in this diagram, it looks like document B and A rank well in both scenarios. So naturally, they float to the top. And then this is kind of finally sent for prompt augmentation. At this point, every chunk is relevant, every chunk is authorized because we've done filtering, every chunk is ranked using multiple signals. This is now the context that the LLM uses to generate your accurate, grounded answers. So we talked about reciprocal rank fusion, and I just wanted to give you, some more details around it. In hybrid search, you can say that the keyword and semantic search will return strong but different results, and combining them without letting one dominate the other is sometimes a challenge. How does it work? So see, you from the keyword search we got document A, B, C, and from the semantic search we got B, D, A. What RRF does is it kind of computes this one by rank formula. So the rank here is 1 for document A, 2 for document B. So this is what I mean by rank. So when we do 1 by the rank, that's the reciprocal part of it. But if you just do 1 by rank, then the document A, the RRF score would be 1. For document B, it will be 0.5, which is a very steep, jump down. So we add a parameter k, so we do 1 by k plus rank, so that acts like a smoothing factor. It's no longer such a steep decline just because it be ranked just next to A. You don't want like the decline to be super steep. So it kind of k helps to kind of normalize those or smoothen the results. Then these documents are combined based on these ranks, and sent for prompt augmentation. Another parameter in hybrid searching that's used is beta, which controls the balance between the retrievers. If your beta is 0.8, then we want it to be 80% semantic weighted versus 20% keyword. So we have that meta parameter or hyper parameter. There are other fusion functions like score-based fusion, weighted linear combination, re-rank, or many different ways, but usually RRF is best choice because of its simplicity and stability. It doesn't matter on individual scores, it just matters, only the rank counts. So it's kind of robust and model agnostic in that way. So RRF doesn't require calibrated scores. But so it makes it more stable than score-based fusion methods when retrievers can behave differently. So that's why it's used. Okay, so now let's talk a little bit about retrieval quality metrics. You've made a RAG system. It's done. But how do you know it's working well? You have to evaluate it. There has to be some metrics that tell you how well it is performing. To evaluate a retrieval, we need 4 things. And this is, I'm talking about more about the accuracy of the results, not about the speed, latency, cost. Definitely those are metrics for any kind of an AI system where you want to measure the latency, the cost, the number of tokens, and everything, and that can be measured too. But in this particular workshop, we're talking about the accuracy of retrieval. So we need four things: the prompt, and the documents returned in ranked order, and the ground truth, meaning which documents were actually relevant, and a way to compare these two, the ground truth and the returned documents. So let's start with some of the metrics. One metric is reciprocal rank. It's similar to the reciprocal rank fusion that you just saw. It's 1 by rank, but it measures the rank of the first relevant document in the returned list. So it basically says how early the first relevant document appears, how quickly does a user see something useful. So if you look at, for example, this table on the right, the first relevant document is at position 1. So its reciprocal rank is 1. Assuming, if you can just for a minute imagine that this was also not relevant, then the first relevant document that came in would be at rank 4. And then the reciprocal rank would be 1 by 4. And that would be 0.25, which is, very small. So it penalizes the retriever on returning irrelevant documents at a higher rank. So that's what it does. Now, precision is the next metric. Precision asks the questions of the documents we retrieved, how many were actually relevant? So it's formally defined as the total number of relevant documents that were retrieved versus the total number of documents retrieved. So that's what mathematically it's defined as. If you have high precision, it means you have fewer irrelevant documents, cleaner context, and less noise will be passed to the LLM. And so there's a lower hallucination risk. But if you have low precision, it means you could have many unrelated documents and there's noisy context. And the model will have to work harder to find the signal. Now, the third commonly used metric is recall. We talked about this precision recall regarding semantic search and keyword search. Recall looks at the problem from a different direction. It says, of all the relevant documents that exist in your knowledge base, how many did you actually find? How many did the retriever actually find? And mathematically, it's defined as the total number of relevant documents that were retrieved over the total relevant documents that exist in your knowledge base. So the high recall really means that important information is unlikely to be missed. Broader coverage of the knowledge base is happening, and there's a safer behavior for open-ended questions. If you have a low recall, then you might miss key documents, or there's going to end up getting you incomplete or incorrect answers, and with false confidence from partial context. So there's this precision recall trade-off happens, and you can usually you kind of use the top K parameter to tune this. Okay, so because most of this is dependent on the number of documents you retrieve also, because you can see the total retrieved is at the denominator. So if you change the K, that will change. That trade-off is also going to change. So you can kind of fine-tune the K. As K increases, recall usually improves and precision often drops. This is like a fundamental trade-off. If you have a smaller K, then you kind of have maybe higher precision. So we're going to talk about a little bit more about precision here. The mean average precision, also known as the MAP, it's always relevant to at K, at what number of documents were retrieved. And this is the average precision for relevant documents in the first K docs. So for example, if you look at this table on the right, precision at K, for the first document, it's like 1 by 1. So you only get one relevant document, and so it's like 1. When you come down, if you have 2K is equal to 2, then here also you only found only one relevant document out of the first 2. So here precision at K would be 0.5. And at 3, precision at 3 would be 1 by 3, because you still only have one relevant document. So it's like 0.33. And at 4, it's like 2 by 4, because now you found another relevant document. So it's like 0.5. Then the average precision is calculated as you're summing up the precision of only the relevant docs and taking an average. So 1 plus 0.5, this is the one relevant doc, and this is another one. And then you get 0.75 as the average precision. And mean average precision is when you basically do this over multiple prompts. So you give it different prompts, calculate the average precision across all of those prompts, and then you average the results over that. The idea here is you want to reward ranking relevant documents high. So good retrieval isn't just about finding relevant documents. It's about finding them early, ranking them consistently, and balancing the precision and recall and K to support high quality generation downstream. So now you're going to go and implement a couple of these metrics with Reena in the workshop over your RAG system.